Word lesson? Yes, I am. I called this types of forces part one. Lesson four is, I think I called it more types of forces or types of forces part two. If you wrap your brain around lesson one, which was Newton's laws, lesson two, which was the concept of a free body diagram, lessons three and four are just going to be various applications that we can handle with a free body diagram, then you're in good shape. We're going to start off with a thought puzzle. It says this. So if I look at the picture, I have in the top picture 4 people pulling on a rope. The rope is tied to a post. In the bottom picture, I have 4 people pulling to the left and 4 people pulling to the right. The tension in the rope in the bottom picture is A, greater than, B, the same as, or C, less than the tension in the rope in the top case. And it says, explain your answer. Shahab, I can tell you want to vote. I hear you wanting to exercise your democratic right. So once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So the top situation, we got 4 people pulling that way on a rope attached to a post. In the bottom situation, I got 4 people pulling to the left, 4 people pulling to the right. The tension in the rope in the bottom case is, who says, Mr. Dueck, it's got to be greater than, because there's 8 people. It's got to be twice as big. Duh. A. No one. Really? Nah, it's the same. You're all correct. I'm proud of you. Well done. Why? Convince me. Nate, I can't hear what you're saying. I'm so sorry. How do you know? Are they accelerating? So in the first picture, that means forces must be. I'm looking for where that starts with letter B. Let's assume all of these humans are identical clones, so like we're getting the same force each way. And let's pretend that these humans are pulling with, I don't know, 4,000 newtons of force, 1,000 newtons each. How hard must this pole be pulling? Sorry for the announcement, those of you on YouTube, but today is grade 9 vaccination day. How hard must the pole be pulling to the right? You said it. 4,000 newtons. Has to be. 4,000. 4,000 newtons. I know, I'm reading out the numbers. That's you sit in the back corner. These guys are still pulling with 4,000 newtons. If they're not accelerating, how hard must these people be pulling with? And you'll notice what I did is I did kind of a quick free body diagram, and the free body diagrams are identical. I ignored all of the rigmarole, all of the stuff, and I said, look, in terms of physics, those are 2 identical situations. Which, ready? If you get this right, we don't have to write out the whole thing. Which one of Newton's laws, Newton's first, Newton's second, or Newton's third, is the one that says if A is 0, forces are balanced? No language, please. Make your guess. Nope. So, because he couldn't guess right, it was Newton's first, by the way. If you knew that was Newton's first, you could write Newton's first. Since he didn't know that, we're going to say A equals 0, so forces are balanced, which is what Newton's first says. Or if A isn't 0, forces can't be balanced. It works in both directions. That's not today's lesson. Today, I want to talk a little bit more about the force of gravity, and then I want to introduce a new force to you. Let's talk about the gravitational force. As a symbol for gravitational force, we're going to use capital F and a lowercase subscripted g. Force of gravity. As an equation, we said, okay, it's going to be F equals, well, technically F equals what? MA. But we said what letter would be a good letter to use for the acceleration due to gravity? So we're going to say the force of gravity is mg. What direction does gravity act? Be stupid obvious. Down, and I'm fine if you say that. I do want to include our friends in Australia, though, for whom their down is our up and our up is their down. So if you want me to be a little nitpicky, I would say toward the center of whatever planet you're on. But if you say down, Tristan, I'm fine with that. This is me being pedantic and nitpicky. What's another word for the force of gravity? Now, all of you look at your formula sheet, please. Look where it says F net equals MA on the front page, about a third of the way down. Right next to it, Alexia, what's another word for the force of gravity? No, now. What's another word for the force of gravity? You said weight. I said no, now. What's another word for the force of gravity? You said weight. I said no, now. What's another word? Have you figured out the dumb joke yet? Okay. I will do that stupid joke every time you say wait. I'll say no, now. And then you'll say no, Mr. Dueck. W-E. Yeah. Another word for the force of gravity is weight, and this is important. You might even want to put a star next to this. I'm going to turn this into a multiple choice question. Here's what I mean. When I ask you to find an object's weight, that's in newtons. Don't give me an answer in kilograms. If I ask you to find an object's weight on your test as a multiple choice question, I guarantee I'll have one of the answers in kilograms for you to pick from. Kilograms is mass. Your mass doesn't change. Your mass on the moon, your mass on Mars, your mass on Jupiter, your mass near a black hole, that doesn't change. That's in kilograms. Which one changes? Which one is location dependent? Your weight. Why? It depends on little g, the force of the acceleration due to gravity at that location. And Tristan, spoiler alert, it's smaller on the moon, smaller on Mars, bigger near a black hole. So Tristan, let's you and I do example 2 together. It says, Shelby the ballet dancer has a mass of 56 kilograms. What does A want me to find, Tristan? So, another word or synonym for weight is the force of gravity. It wants me to find mg. What's the mass? Good. What's g? You've probably still got it memorized. If not, it's on your green sheet if you forget. Probably about a third of the way down on the front page. When you see it, you'll go, oh, yeah. Yeah. What is G as a number? Yeah. So it's going to be 56 times 9.8. How hard is the Earth pulling her down? What do you get? I can do this in my head. It's going to be 560 take away 11.2. It's going to be 549. Is it 548.8? Yeah. I'd probably on a test write that as 549 newtons if it was multiple choice. That's her weight in newtons. That part you will need to kind of commit to. Well, wait a minute. Did I actually give you the word weight on your formula sheet right next to where it says mg? So I don't know how much you need to commit that to memory, Alexia. As long as you know it's on your sheet, it's kind of there. Yes. Now, the SI unit for weight is newtons. The SI unit for weight, sorry, the imperial unit for weight is pounds. Pounds is force in the imperial system. It's the newtons of the imperial system. So we still, for some reason, do most of our weight in pounds, not in kilograms mass or in newtons weight. So given that 1 kilogram of mass corresponds to 2.2 pounds at the Earth's surface, what is Shelby's weight in pounds? If I was doing this, I would fall back to my old unit conversion days. I would write down what they gave me, which was 56 kilograms. I want kilograms to cancel. Nick, where am I going to put it in my conversion factor? On the, remember these tricks? And then pounds, I told you an abbrev for pounds is what we used to call the pound sign, the number C key. What am I going to put? What's my conversion factor? What am I going to put next to the pounds? Question told you. Yes. And 1. Yeah. If you want to convert kilograms to pounds, it's times by 2.2, which is what? I can do this in my head. It's going to be 112 plus 11.2 is going to be 112. It's going to be 120. Is it 123.2, I think? Yeah. And we'd probably round it off to 123 pounds. Marcus, what would Shelby's mass be on the surface of Jupiter? Too slow. Ryder, what would Shelby's mass be on the surface of Jupiter? Too slow. Arnica, what would Shelby's mass be on the surface of Jupiter? When I do my dumb too slow, what I'm saying is you already know the answer. What's Shelby's mass on Jupiter? Chaz, of course it's 56. Your mass doesn't change anywhere in the universe. Which one changes? Not your mass. Which one changes? No, now. Which one changes? No, now. Which one changes? It's a stupid joke that I'll do to help you remember the term weight. Okay? Yeah, weight. Your weight is the one that changes. And so, D, what would Shelby's weight be on Jupiter's surface? Mr. Dueck, Jupiter doesn't have a surface. It's a gas giant. Good point. But let's pretend we were floating like a spaceship right on the surface of Jupiter and she was standing inside the spaceship. How heavy would she feel? What would her weight be? Where G is 25, it would be 56 times 25, which is what? Do that one in your head, Mr. Dueck. What's a good way to multiply by 25? Divide by 4 and then times by 100. So it's going to be 14 times. Is it 1400? What was her original weight on Earth? 549. 1400. She's feeling, well, about 2.5 times her weight. 25 meters per second squared. That's around 2.5 G's-ish. How many G's are you all pulling right now just because you live on Earth? So Shelby would, yeah, you're all pulling 1 right now. Shelby would feel like an extra 1.5 of her were getting piggybacked on her back. All of you would feel like you were giving a piggyback to yourself and half of yourself. You could function-ish. You wouldn't die. Everything would be awkward and horrible and you would get tired really, really quickly. But certainly for a couple of hours, you could survive in that gravitational field. It would just suck. Okay? Weight, the force of gravity. Weight, not kilograms. The next force I want to introduce to you is something called the normal force, but we need to build to it. Suppose a 12,000 Newton truck is sitting at rest on the ground. Draw a free body diagram of the forces acting on it. Okay, here's the truck. What are the forces acting on it? Salmon, get the obvious one. Which way? Yep. Oh, and you know what? I'm going to write mg, but I know how big it is. Because what are the units next to that 12,000? That's the weight. Gravity is pulling down with 12,000 newtons. Mr. Dueck? Yes, Salmon. If I know the weight, how can I figure out an object's mass? So if you want to, I know you all turned the page, if you want to on the previous page, you can make a little note that m is the force of gravity divided by 9.8 on the Earth or whatever planet you're on. If you ever need an object's mass and they give you the weight, it's pretty trivial to find the mass. Okay, let's go back to here. This can't be right because which way would this be accelerating if that was the only force acting on it? Are we sinking into the ground like quicksand? Are we flying here like Superman? So it's going to be an arrow pointing up, bigger, smaller, or the same size? Okay. What force is that? We're going to give that force a special name. Anytime a surface prevents you from sinking into it, so all of you right now, can you do me a favor? Lift your feet up into the air. Seriously. Can you feel the chair preventing you from sinking into the chair now? Or if I'm standing right here, I can feel the ground pushing up through my feet, preventing me from sinking into the ground. Or if I push against this wall, I can feel the wall pushing back on me. Anytime, any surface that prevents you from sinking into it, we call all of those the normal force. We would call this Fn, and it would be 12,000 newtons. We just lump any surface generically into that. That way, who did I have standing on the table the other day glaring down at all of us? Was you? Yeah. So the table, we called it F table. I would have just said, you know what? It's a surface. It's a normal force pushing up through your feet. Suppose we add a 2,500 Newton piano to the back of the truck. Draw a free body diagram now. Okay. What are the forces acting on this truck? Get the obvious one, Ryder. Yeah, which way? And I can even tell you how big it is. mg is 12,000 newtons. Also pushing down on the truck now is the piano. The weight of the piano I'm going to put it right next to it. I'm going to draw it smaller because it's not as big as the 12,000. And I'm going to call it F piano equals 2,500 newtons. Nate, that's a 2,500 newtons. I'm having to write small to fit it in on my diagram. 2,500 newtons. It's piano pushing down. Okay. Ryder, is this truck sinking into the ground like quicksand? Is it flying here like Superman? Means forces must be where it starts the letter B. There's an arrow going to be pointing up. It's going to be the ground, the normal force pushing up. Bigger, smaller, or the same size as that 12,000? Has to be bigger. In fact, I can even tell you exactly how big it is. It's 14,500. If I was trying to be fussy, I would draw the upwards arrow as long as these two downwards arrows added together. I said roughly to scale. I'm just going to make it stupid obvious that it's larger. And I'm going to say, okay, here the normal force is 14,500. I know it has to be there because Cole, if it wasn't, the truck would be sinking into the ground like quicksand, or it would be flying into the air like Superman. The force of the ground, or any surface, a table, a chair, etc., pushing up to prevent an object from sinking into it has a special name. We call it the normal force, symbol Fn. Why do we call it the normal force? The word normal in math means at right angles to. If this is the ground, the normal force is pushing up at a right angle. In other words, when you're standing, you don't feel the ground pushing you sideways at an angle. It's pushing straight up on you. Or if I'm pushing against a wall, Geo, the normal force is pushing straight out from the wall at a right angle. It's not pushing at an angle. So the word normal in math is one of the many words that means perpendicular to, or at right angles to, or orthogonal to, or tangent to. There's a bunch of words that mean at right angles to. And we'll symbolize it capital F with a subscripted N. Put your pencils down. There used to be a Physics 12 provincial exam, and so kids would write the provincial, and then some of us teachers would mark it in the summer. I was on the marking committee for a couple of years, and I was marking one kid's test, and the question said, find the normal force. And a student wrote, which was funny. I marked it wrong. They got 0, but it was at least, I mean, okay, they knew the symbol. I guess that was some improvement. Some of you are still trying to figure out the joke. Okay, don't say it out loud. You'll just figure it out yourself. Alrighty. The normal force, how hard the ground pushes up, it's a reactive force. What does that mean? It's a consequence of Newton's third. What was Newton's third law? It's okay. I didn't tell you had to memorize it. I'll give you a hint. Forces come in pairs. Because it's a reactive force, it's only as big as it needs to be. Let's suppose that I right now am pushing down on the ground with 2,000 newtons of force. Am I sinking into the ground like quicksand? Am I flying through like Superman? So Alexia, if I'm pushing down with 2,000 newtons of force, how hard exactly must the ground be pushing up with? 2,000 newtons. What if I'm pushing down with 2,001 newtons? The ground is pushing up with 2001. The normal force is as big as it needs to be until it can't match the downwards push, then you'll sink. Or if you're standing on a table, the normal force will push up until it can't match it, then the table will break. We've just explained how you break something by standing on it. You ask that object to try and give a normal force bigger than it could. Then Newton's first kicks in and you accelerate. So it's as big as it needs to be. Look at your formula sheet. Is there an equation for the normal force? Is there an equation that says Fn equals something, 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 something along that line there? Nope. The only way to find the normal force is from a good free body diagram. Like example 3. I like example 3. It says, how big is the normal force in each of the following situations? So this first one here, they want us to find the normal force. This is a job for a free body diagram. Although, Shahab, did they give me a picture? I'm going to label the picture. First thing, we get the obvious one, Shahab. What are the forces acting on this 10 kilogram mass? Get the obvious one. mg, and I can even tell you how big that is. On my calculator, I'm going to go 10 times 9.8. Should be 98, I think. Yes? Is this box sinking into the ground like quicksand? So there must be an arrow pointing up, bigger, smaller, or the same size as 98. So we're going to say, here's the normal force, and I can even tell you it's 98 newtons if I need that piece of information. Okay. In situation B, Cole, there's an extra force down, an extra 30 newtons. So what are the forces acting on this? We have gravity down, which was 98 newtons. And then we have this extra force down. I don't know what that is. Usually we call a mystery force, we label it F applied. Something is applying a force. Maybe it's an invisible little leprechaun. I don't know. But I can tell you what the total force down is. What's the total force down, Cole? You might be able to do it in your head or use a calculator. 128. Is this mass sinking into the ground like quicksand? Is it flying here like Superman? It means vertically forces must be. I'm looking for the starts with letter B. So I'm going to draw an arrow pointing up, bigger than the 98. In fact, how big will the arrow pointing up be exactly? Yes. Normal force here has to be 128 newtons. Otherwise, this can't work. In this third situation, something is lifting up with 50 newtons. We still have, get the obvious one. That's a mistake. Someone hit the wrong button. We still have, get the obvious one, 98 newtons. They're going to tell us to ignore that. Yep, waiting for the announcement. Okay, they're going to try again. Meanwhile, we're going to keep teaching. What's the total force downwards here, Adam? Oh, here we go.
If you last names E, Q, and R, please report to the mini gym. That's any grade 9 last names E, Q, and R, and we apologize for Miss Means and her shenanigans.
Alrighty.
Also, any grade 8s to 12s, if you think you might need a shot that you missed, or you have questions about shots, you can head to the mini gym as well.
Okay.
Thank you.
Adam, back to what I was asking. What's the total force down in newtons? Right, yep, you're correct. And then something is lifting up, 50 newtons. So how hard does the ground have to push up to cancel out gravity? Not 98. Yeah, and I'm going to make it stupid obvious. I'll make the normal force way smaller than gravity, and I can say Fn equals, if I need it, 48 newtons. Okay. Question. When you stand on a bathroom scale, what does a scale measure? Got to pause the YouTube video for just a second, sorry. So, a scale does not measure mass or weight. Nick, what does a scale measure? It measures how hard the ground is pushing up through you, through your feet. So when I ask you to find what a scale is reading, which force are you going to get by itself? What am I really asking you to find? So, by the way, when I jumped out of an airplane, when I jumped out of an airplane, had I stood on a scale while in free fall, what would the scale read exactly as a number? 0. So physicists will talk about another phrase for the normal force. We'll call it your apparent weight. Your true weight is mg, but that's not actually how heavy you feel. You feel as heavy as the ground is pushing up on you. Everybody lift your feet up off the ground right now. Your weight didn't change, but your brain thinks you got heavier because more of the ground is pushing up, more of your chair is pushing up through your body. When your feet are back down on the ground, then you're splitting it between your feet and your body. So your apparent weight is how hard the ground is pushing up on you. That's the normal force. I felt weightless when I jumped out of an airplane. Why? No normal force. Still gravity. No normal force. And this is important because all a good amusement park ride does is it mucks around with the normal force. We can't change mg, we're not God, but what we can do is change how hard the chair of the ride that you're sitting in pushes up on you. We can put you into a partial free fall where the normal force will get less, or we can have you accelerate up where the normal force will get more. We can make you feel heavier. We can make you feel lighter. Has your mass actually changed? No. Has gravity actually, your weight actually changed? No. What's changed? Normal force. Put your pencils down, look up. This is a video of a little kid's first roller coaster ride. See if you can figure out when the normal force changes. There's going to come a moment in time when you're going to sense that the child has just experienced a normal force changing for the first time. See if you can spot it.
Great.
Good high roller coaster. So again, you're looking to see if you can spot when the normal force changes.
Over the top. Get your hand in. Here we go.
If I had to make a guess, about there? Yeah? What's this kid feeling, heavier or lighter? You've been on roller coasters. When you go over the first hill, do you feel heavier or do you feel lighter? Someone said heavier, someone said lighter. The good news, one of them is correct. I know he's not feeling his normal. He's not feeling mg. Why? He's in partial free fall. Not full free fall, but certainly partial free fall. He's accelerating downwards. He's feeling lighter. And this is scary because...
Last name S.
Okay. Okay. Boy, this is going to be a great one for YouTube that I'm uploading, but such is life. All of you, when you're little kids, when you're horsing around, there are lots of experiences where you feel heavier. When you piggyback someone, you feel the ground pushing up heavier through your feet. You feel heavier. Or when someone dog piles on you, at the bottom of a swing, you feel heavier when you're swinging. There's not many spots where you feel lighter. At the top of the swing, you feel a bit lighter. That's the stomachy feeling at the top, but you've got chains to grab on. There are some times when you're in free fall, if you're on a trampoline while you're in the air, or if you're jumping off of a high dive, although a lot of kids won't jump off of a diving board because that's scary. There's not many experiences where you feel lighter. This kid is feeling a lighter than normal. I could not show you this video in good conscience, though, because this kid is scared. Watch one of the best recoveries you'll ever see. I'm actually really proud of this. Because he's scared right now.
You okay? Oh, we're going again!
He's scared. He's scared.
Hold on, buddy.
Right here. He gets his hands up.
Boys!
amusement park ride that moves up and down vertically, all they're doing is changing the normal force. They can make you feel heavier, like at the bottom of the pirate ship. They can make you feel lighter, like at the top of the pirate ship swing. Can't change gravity. We can change how hard your chair or the surface that you're standing on pushes up on you, and that's the normal force. Elevator questions are nice thought puzzles. In fact, you're going to get a bunch of elevator questions on your test. Let's look at the situation. It says this. In each of the following situations, will a scale reading show a person's normal, mg, more than mg, or less than mg? This is a job for a free body diagram. I'm going to zoom in and I'm going to actually draw my free body diagram right on the picture here. What are the forces acting on this girl right now? Get the obvious one. Get the obvious one. Gravity, which way? So mg. In the first picture, is this girl accelerating? So forces must be, I'm looking for where that starts with the letter B. So I'm going to draw an arrow pointing up, bigger, smaller, or the same size as mg. In the first picture, she would feel her normal. She would have no way of telling if she was moving or if she was at rest because the scale would read the same. Einstein talked about that in special relativity, as a matter of fact. What about this second picture? Which way are we accelerating in this second picture? Up. So what are the forces acting on this girl? Get the obvious one. Which way? What else? Which way are we accelerating? Which way must there be an unbalanced force? Same answer. Which way must there be a longer arrow? Same answer. So yeah, I'm going to draw a normal force, but it's going to be, and I'll exaggerate it, it's going to be much larger than gravity. So in this picture, does she feel heavier, lighter, or the same? She'll feel heavier. And the scale would read heavier because scales don't measure mass. They measure normal force. What about in this third picture? Which way is she accelerating? Down. What are the forces acting on her, Marcus? Get the obvious one. Which way? Yep. What else? There is still a normal force. The scale and ground are still pushing up through her feet. Bigger, smaller, or the same size as mg? Yeah. So here, does she feel heavier or lighter? And that's the one most people get scared by. That's the one that seems to be wired into us. We don't like it when the floor drops down. We're okay with the floor pushing up, but dropping down, that's where more people are, yeah. Oh, what about this situation here where the rope snaps? What are the forces acting on her? Get the obvious one. Yeah. What else? It's a trick question. Nothing. And so, first of all, is gravity acting on her? Does she feel any weight? No. She feels like she's floating. This was what Einstein called his happiest thought. This is what led him to get general relativity when he realized someone falling in an elevator would be floating. Even though we see gravity acting on her, she can't feel it. Because what you all feel of as your true weight is actually your apparent weight. It's the normal force. Let's look at some elevator questions with numbers. I like example 4, I like example 4, I like example 4. In fact, you know what? There's going to be at least 4 elevator questions on your test. I'll bet you in one you're accelerating up. I'll bet you in one you're accelerating down. I'll bet you in one you're not accelerating. And I'll bet you in one the rope is cut and you're in free fall. So, example 4, a 72-kilogram man stands on a Newton scale. What do I mean by a Newton scale? Instead of a regular scale that displays kilograms, where you'd have to multiply by 9.8 to change it to newtons, it displays newtons. What does the scale read if the elevator is, okay, Gio, which way are we accelerating in part A? This is a job for a free body diagram. What are they asking me to find, Gio? Read me the what does sentence. What are they really asking me to find if they're asking me to find a scale reading? No, not the mass. Scales don't measure mass. Scales don't measure weight. What are they really asking me to find anytime they're talking about a scale? The normal force. Good. You have an FN clue. Excellent. Here's our free body diagram. What are the forces acting on this girl, Gio? Get the obvious one. Which way? Yep. mg. Which way is she accelerating in part A? Which way is there going to be a bigger arrow pointing? Which way is there going to be an unbalanced force? Which way is the winning direction? All the same answer. I'll exaggerate it. Which force is that? Well, it's the scale pushing through her feet. But Gio, what were you clever enough to realize that that force was the same as? Okay. Which force is this? It's the scale pushing up between her, underneath her feet. But what did you realize that that's the same as? Which force? Yes. And then you were away for this next part, but Maddie wasn't. Maddie, what was our template? Winner minus loser equals what? Who's winning? Good. Who's the loser? Salmon, did you see? I asked her who the loser was, and she looked at you. Wow. Fine, Maddie. Who's the losing force? Minus mg equals what? ma. Gio, coming back to you. What did you say that they were asking us to find when it said, what does the scale read? Get the Fn by itself. How would I move the mg over? What's right in front of the mg? Yes. It's going to be ma plus mg. I'm just going to memorize. You cannot memorize these because I'll keep giving you new and changing situations. What you want to memorize is, this is a job for a free body diagram. Who's winning? Who's winner minus loser equals ma. What's m, Gio? They told me. What's the mass? M, they told me. Yeah, you went and looked for kilograms. What's the acceleration? They told me. You went for looking for meters per second squared. Good. Plus, what'd you say m was? 72. Tristan, what's g as a number? Yes. How hard is the ground pushing up? What is the scale reading? How big is the normal force? That's all the same question. I just phrased them differently. I might be able to do this in my head because it's going to be 72 times 13. 720 plus... Now, what'd you get? 936. Anybody else? Units. It's a force. Good. Could you do me a favor? Go answer button divided by 9.8. If the scale measured kilograms, how many kilograms does she feel like her mass is now? Arnica, what'd you get? Yeah, her actual mass is 72. She feels way heavier. Okay. She would feel like she was getting pressed down. That's because your body is a backwards accelerometer. She's getting accelerated up. That was accelerating upwards. We just did, B is also accelerating upwards. I'm going to gamble and skip B, and I'm going to go to C where we're accelerating downwards because B and A are kind of the same. Banner, it still wants us to find the normal force. So you know what? There's no equation for the normal force on your green sheet. Why? Because this is a job for a free body diagram. We're going to have to figure it out. So here's this person. What are the forces acting on them? Get the obvious one. Gravity. Which way? Okay. What else? How do I know there has to be another force? If there was no other force, if it was just gravity, what would that number there be exactly, Tristan? No. If there was only gravity, what would that acceleration be exactly as a number? I keep coming back to you with the same question. Figure it out. If it said 9.8, then I would know no other forces but gravity. It's less than gravity. Something's slowing us down. So there is an arrow pointing up. What force is that? Bigger, smaller, or the same size as mg? How come? Which way are we accelerating? So that must be the winning direction. I'll exaggerate it so it catches my eye. Who's winning? Who's losing? Winner minus loser equals MA. What am I trying to find? What's right? I want to get the Fn by itself. What's right in front of the Fn that I don't like? A negative. Anytime I have a negative term that I'm trying to get by itself, I refuse to deal with it. I'll plus it over to the other side. At the same time, how will I move that MA over? Because there's an invisible plus sign there. My students a few years ago nicknamed this little move where we plus the term to the one side and minus the other term over. They nicknamed this the swappy dance because they said, Mr. Dueck, the MG drops down, but then the MA and the FN swap places, except, wait a minute, instead of putting equals FN, let's put FN equals over here where we're used to seeing the thing by itself by itself. But yeah, they swap places. And now we're good to go. What was the mass? Was it 72? G, 9.8. And again, I don't need to worry about the negative. In fact, we decided to let down be positive in this question because it made the math easier. Minus 72 times 5.2. How hard is the ground pushing up on this girl's feet? How hard is the normal force? How big is the scale reading? All the same thing. What'd you get? 331.2 newtons. On a test, if this was multiple choice, I'd probably just go to 3 sig figs as your answer, but we'll keep it all in there. Because there's a second part. It says, what would the scale read in kilograms? How do I convert newtons to kilograms? Tristan, what will I divide by to convert newtons to kilograms? Tristan, you've had the same line the last... What? Because mg is what we did to get fake gravity, divide by 9.8 to get fake mass. So can all of you go answer button divided by 9.8? We can say this, scale equals 331.2 divided by 9.8. What'd you get? Banner, what'd you get? 33. She feels like she weighs 33.8 kilograms. She feels lighter. By the way, it's usually around now, I should point out, no public elevators accelerate at this rate. If you were in an elevator that accelerated down at 5.2, everybody would start screaming in terror. It would be panic. Most elevators accelerate like 0.1, 0.2. This here, much closer to the elevator, say, which is not meant to be a casual ride that you want to put senior citizens on to get to their floor of their building. Right? It's meant to be a thrill ride. I should point that out. Arnica, which way are we accelerating in part D? Which way did we accelerate in part C? I'm going to gamble that you can handle part D. I'm going to skip it. I'm going to do E and F, and then we're going to press pause. E says, what if moving downwards at a constant velocity of 3.2 meters per second? Do you see the key phrase that's ding, 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 ding we need to be paying attention to? Nope. Oh, that, yes. What does constant velocity tell me? And in terms of Newton's laws, if A is 0, that means forces are? This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. What else? Normal force. Which way? Up. Bigger, smaller, or the same size as mg? Why? Constant velocity. Now, a lot of students see the word downwards and they want to make gravity bigger. No, constant velocity. The normal force is going to be the same size. In fact, my equation here isn't going to be winner minus loser equals ma. If forces are balanced, it's a tie. The normal force equals mg. That's what all of you experience as your normal. What was M? 72? G, 9.8. What do you get? It's going to be 720, take away 14 is 716, take away, is it 715? What'd you get? I did carried a 1 wrong. Wow, 705.6. Would this person feel any different than if they were at rest? Nate? No, this is what Einstein said as well. If there's no acceleration, you can't tell the difference between moving and at rest. There's no difference. We only can detect acceleration. Nate, what would the scale read if the elevator was accelerating downwards at 9.8 meters per second squared in free fall? What would it read exactly as a number if you tried to stand on it? First of all, how would this happen? Cable snapped. Okay. Elevator is plunging down. How heavy will you feel? What will the scale read? Shahab. What? Loud and proud. Yeah. You can do a full free body diagram and prove it when you solve for Fn, you'll get 0. Yeah. Not true weightlessness. True weightlessness is when you're in the middle of intergalactic space with no gravity, but apparent weight. You'll feel weightless in this situation. We're going to pause here. We're going to finish this off next class. If you want to get a head start on the homework, especially if you know that you have tomorrow off and you're going to be busy later on in the week, section A, you can do every question. You can circle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In fact, I'm going to be assigning every single question, even in section B too. Section A, it just wants you to circle the correct answer. Let's do number 1 together. It says, comparing the concepts of mass and weight, one of these is basic and fundamental, depending only on the number and type of atoms that compose it. Which one is fundamental, mass or weight? Mass, circle mass. And it's kind of walking you through all of those for the next 10 questions. Okay? Circle the correct answer. Also, I know many of you are still working on lesson 2. Yep, we can work on that. Some of you are still working on lesson 1. So I'm going to pause here. Next class, we'll talk about why the astronauts float on the International Space Station. It is not because there's no gravity. If you ever watch any of the astronauts when they're on the space station, they'll always talk about microgravity, which is what they're in, not no gravity. There's plenty of gravity up there. G up there is about 9.2, not 9.8, but pretty close. So then why the heck are they floating? That's a good question. Stop.